So in this video we're going to have a look at rates of change by looking at a simplified one-dimensional motion where some object increases its velocity for a period of time from 0 to 8 meters per second and then travels at constant velocity for a period of time after that. We're going to make a displacement time graph out of that, and by displacement we mean how far something is away from its starting point. And we're also going to make an acceleration time graph, and we'll look at what acceleration means when we get to it. So starting off, the easiest place to start, funnily enough, is the second part of the motion. Here we go. So it's travelling at 8 meters per second and it's doing it for 6 seconds. Now what we have here is a change in displacement then of 48 meters, because something's moving at 8 meters every second and it's doing it for 6 seconds. A couple of things to point out. First one is the use of the delta symbol to mean change in. So there's going to be a change in displacement of 48 meters when we come to the displacement time graph. And another really key thing is that we haven't coloured the green thing in by accident. That rectangle there has an area of 48. So the area underneath the graph tells you the displacement. Okay, now so we've got this 48 meters, but we don't know exactly where it goes on this displacement time graph because we haven't looked at the first part of the motion yet. So let's do that now. Well, the first part of the motion, the area underneath it is a triangle. And going by the clue from the rectangle earlier on, we might expect that the area under the triangle tells us the distance travelled, or the change in displacement, in that 4-second period at the start. And we'd be right. And we could calculate the area of that triangle really easily because we know how to do that. It's half the base times the height. So it's a 4 by 8 triangle, so that's 32, half of that, 16 meters covered in those first 4 seconds. Another interesting way of looking at that is that those 16 meters are exactly what would have been covered if the object had been travelling at the average speed all the way through. So there a 4 by 8 triangle is identical in terms of area to a 4 by 4 rectangle. Now we know the distance travelled, or the change in displacement in that first section of the graph, is 16 meters. We can put that 16 meters on the displacement time graph. And then we know that the second bit of the motion had a change in displacement of 48 meters, so we can move up 48 meters and then join those points with a straight line. And we know we join them with a straight line because the velocity is constant there, so the displacement is changing uniformly. There we go, there's 48 meters displacement. And another really key point here is that in just the same way as you can get the change in displacement from the area under the velocity graph, well, you can also get the velocity from the gradient of the displacement graph. Here's a line where the change in displacement is 48 meters, as we know, and the change in time is 6 seconds. So the gradient of that line is 48 meters over 6 seconds gives you 8 meters per second. But we know that the 8 meters per second is exactly what the velocity is in this section of the motion anyway. Now let's have a look at what happens in the first part of the motion on the displacement time graph. We've already said that the gradient of a displacement time graph is equal to the velocity, and we also know that in the first part of the motion the velocity is increasing. So that means that on the displacement time graph the gradient should be increasing as we get from 0 to 4 seconds, and if I'd managed to draw it any better than that, it would have seamlessly joined up and been a perfect curve. Okay, now we know that. We've finished the displacement time graph now. We can have a look at what happens to the acceleration. Now acceleration is the rate of change of velocity. In just the same way that velocity is the rate of change of displacement, and we can calculate that from the gradient of the displacement time graph, well, so acceleration is rate of change of velocity. So let's, as we did before, do the second part of the motion first. Well, the second part of the motion, the velocity wasn't changing, so there's no acceleration. And in the first part of the motion, the velocity was changing, and it was changing uniformly. Look at the straight line. It was changing by 8 meters per second in 4 seconds. So that means that in every second the velocity was changing by 2 meters per second. Or in other words, there was a rate of change of velocity of 2 meters per second every second, or 2 meters per second, if you like. So let's summarize. Starting with displacement, the rate of change of displacement gives you velocity, and you can find that from the gradient of the displacement time graph. Also, if you're measuring displacement in meters, that means that the velocity will be measured in meters per second. You can get back to a change in displacement from a velocity time graph by calculating the area under the velocity time curve. And similarly, acceleration is the rate of change of velocity. So if velocity is being measured in meters per second, then acceleration is being measured in meters per second. And this is just a nifty way of writing that with the -2 in the exponent. So that's it for rates of change, and we'll see these ideas in future videos when we start to look at calculus